We now want to introduce something called an antiderivative. And as the name would kind of imply, the antiderivative is just the reverse of taking a derivative. In other words, on occasion, we have a function, we want to know how it's changing. Therefore, we want to take a derivative. Derivative gives us instantaneous rate of change. But on other occasions, we know how things are changing. We know the derivative. We know the slope, in other words, and we want to go back and say, okay, what is this the derivative of? In other words, f of x is an antiderivative of f of x, and it will be common to use the large f to symbolize the antiderivative of small f, at least for the time being. That is what will be done. But anyway, large f is the antiderivative of lowercase f if taking the derivative of uppercase f results in a lowercase f, all right? Now, for the time being, what will happen, the way these antiderivatives will be found is that you will simply have to look at a function and say, well, what would I, or what have I in the past perhaps taken the derivative of to get this answer? For example, if you had f of x equaling something like x squared. Well, when we take a derivative of a polynomial, we have a polynomial in particular, but not exclusively, we have a power rule that we use that basically says, if I was to take the derivative of x squared, the power would drop down by 1, so we would go from a second power to a first power, and that power, that square, would go out front and become a coefficient. So if taking a derivative drops the power by 1, then the antiderivative, it would only be logical to assume that the antiderivative would raise the power by 1. So an antiderivative of an x squared must involve an x cubed. The problem, though, is if I try to take the derivative of this, yes, the third power drops to a second power. That part's good. But I'm going to have a 3 out front. I'm going to have a 3 out front that was not found in the original function. So the antiderivative rule would say, or is going to come to say, to remedy that problem, we just divide. So with a derivative, the power comes out front. With the antiderivative, it goes on the bottom. All right. So again, if you note that taking the derivative of f prime, taking the derivative with respect to x, in other words, of an x cubed over 3, would give me a 3x squared over 3. 3's cancel, and you get the x squared. All right. So in general terms, if your original function is x to the n, and of course this won't work for, this isn't going to work for n equal -1, and we'll get around to that as to why. But if your original function is x to the n, then the antiderivative of that is going to be x to the n plus 1 over n plus 1. Again, meaning the power goes up instead of down, and you divide by it instead of putting it out front as a coefficient. All right. Now, something else, though, that maybe you hadn't noticed, if you again look at f of x equals x squared, I'm going to suggest that there's another possibility for the antiderivative. And that possibility is x cubed over 3 plus 5. Remember, the definition of antiderivative is that you simply need to be able to take the derivative of it and get that result. And when I take the derivative of that f prime, when I take the derivative with respect to x of an x cubed over 3 plus 5, I once again get an x squared simply because the derivative of 5 turns into a 0. So the language, the terminology that you're going to see is that when they, at least for the time being, and it's actually not going to be a short-term thing, but when they ask for an antiderivative, they will ask for the most general antiderivative. And hopefully you realize that if this was a plus 5 or a plus 6 or a plus 7 or a plus of pi or a minus of 3, taking the derivative would get me the same x squared every single time. So what actually can be proven is that if you have a function and you find its antiderivative, that antiderivative and all other antiderivatives only differ by a constant on the end. That can be the only difference between them. In other words, the most general antiderivative of x squared is x cubed over 3 plus an arbitrary constant, right? And that's going to be something that you'll find that people are a stickler for that. You have to include that constant when you're talking about a general antiderivative. The constant has to be there. And again, what the constant is telling you is that all antiderivatives of x squared are of the form x cubed over 3 plus some kind of a constant. And the constant can literally be anything, but it is the fact that they all differ by nothing more than a constant. Now, that may make you think that they all look exactly alike. Well, no. When we get into things like trig functions, you're going to find that two antiderivatives can look very different. That the fact that the constants vary can give a very different appearance to your answer, but that's not something we need to worry about right now. That's going to come up later. But as I said previously, what you will find is that at least for some time that you're going to evaluate antiderivatives simply by looking at it and saying, well, what did I take the derivative of to get that answer? For example, f of x equal 1 over x. What did you take the derivative of to get 1 over x? Think about it. I'm hoping you won't have to think very long. You realize that that's just natural log of absolute value of x. All right, which is why I said when x is -1, because when the power is -1, because that's equal to x to -1 power. That rule that I showed you does not apply when the power is a -1, because that's a logarithm. All right, so that natural log absolute value of x is an antiderivative. The most general has a plus c on it. If f of x was e to the x, I hope you know that you take the derivative of e to the x to get e to the x. And I hope you remember that the c is required. If f of x was equal to cosine of x, I hope you remember that you take the derivative of sine of x to get cosine of x. And I also hope you remember to give the c so we can have the most general form. Okay, if f of x was equal to secant square of x, I hope you remember that you take the derivative of tangent to get secant squared, and don't forget that constant. There are quite a few. Every derivative that you have memorized is now something you have to use. That memory you have to pull up for integration purposes. One that they love to put a lot of use, get a lot of use out of 1 over 1 plus x squared. And I hope you remember that you take the derivative of inverse tan of x to get the 1 over 1 plus x squared. And again, There are many more that I could name, too many for me to sit here and list. But again, everything that you've ever gotten in the form of a derivative will now be thrown back at you in the form of an antiderivative. I want to go to, I've got an old copy of the book here. I just want to go through a few problems to show you how quickly you should be able to do this, right? If f of x is equal to x minus 3, what would its antiderivative be? Well, remembering that you can differentiate its sums and differences individually, one at a time, that should lead you to the conclusion that you can anti-differentiate them the same way. So the antiderivative of the x is the x squared over 2. The antiderivative of 3 is a 3x. And don't forget the constant, so we can have the most general form. All right, so again, if I had an 8x to the 9th minus a 3x to the 6th plus a 12x cubed, the antiderivative of that, going one item at a time, all right? The constant out front, when you take a derivative, just stays sitting out front. Power goes up, and you divide. Constant out front stays out front. Power goes up, and you divide. Constant out front stays out front. Power goes up, and you divide. Don't forget the constant. All right, and then, of course, since we always want to clean things up as much as possible so we have the neatest conceivable possible answers, we reduce the fractions. 4/5 x to the 10th minus 3/7 x to the 7th plus the 3x to the 4th plus the constant. All right, again, you can differentiate this answer and quickly check it to see that it is right. All right. Try a couple more just for practice. What would we do with a 5 minus 4x cubed plus a 2x to the 6th over x to the 6th? Well, if you recall your quotient rule for derivatives, it's quite complicated. It is sufficiently complicated that you will never see a quotient rule, or for that matter, a product rule for antiderivatives. All right, the rules that exist are so complicated, there is no backwards way of undoing those. So for this, I'm going to have to get creative. I'm going to have to bring the 6 up as an x, the x to the 6th up as an x to the negative 6th, and distribute it. In other words, this will become 5x to the negative 6 minus 4x to the negative 3 plus a 2x. I just brought that 6 power up, and that's what I got. This I can work with. All right, this I can find the antiderivative of. That, no way, can't do it. All right, so the antiderivative of this time, again, remember the power out front stays out front. This power increases by 1, and you divide by it. Power out front stays out front. Power increases by 1, and you divide by it. Number out front stays out front. This increases by 1, and you divide by it. Don't forget your constant. And then you simplify. 5 over negative 5 is a negative 1. Put the power back down on the bottom. You don't absolutely have to do that. All right, but it's a good idea. 2 negatives make a positive. 4 over 2 is 2. Put it back down on the bottom. 2's cancel. And there's your constant. All right, so this rule is something you will have to get accustomed to very, very quickly. You're going to have to get used to it. You're going to have to get used to it in a hurry. All right. For your antiderivatives, again, for the moment, we simply have to memorize what did I take the derivative of to get this answer. And this can be used This is used not just for first derivatives, but it's used for second derivatives as well. So let's skip down the page and look at some second derivatives. If I have second derivative of f equaling 2 plus x cubed plus x to the sixth. If you're being asked to find f, they do not use that large F notation simply because it would get too confusing when you're dealing with a second derivative and beyond. So what you'll have to do, there is absolutely no way to jump from a second derivative straight back to the first. From the second derivative, you have to step back to the first, and then you can go back to the original function. So the antiderivative of 2 would be a 2x. The antiderivative of x cubed would be an x to the 4th over 4. The antiderivative of x to the 6th would be x to the 7th over 7. And don't forget the constant. Stepping back once more, the antiderivative of 2x is x squared. The antiderivative of x to the 4th over 4 is x to the 5th over 20. Do you see where the 20 came from? I hope so. I took the 4, bumped it up by 1, moved the 5 down to the bottom, and 5 times the 4 that was already there. There's where your 20 came from. This being x to the 8th over 56 plus, and here's where we're stepping into a new idea here, a new concept here. This constant has the antiderivative has to be found. And the antiderivative of a constant is a constant times the variable. Take the derivative of this, and you'll see that you get that. And every time you find the antiderivative, there is a constant involved. So we use the notation C sub 1, or C1, to say that the constant from this antiderivative is not necessarily the same as the last. As a matter of fact, it's definitely not the same as the last. It can be done on second derivatives, and it can be done on third derivatives. If you had f triple prime of x equaling e to the x, could you work your way back to the original function? Yes. Stepping back once, f double prime would be e to the x, again, because derivative of e to the x is e to the x, therefore the antiderivative of e to the x is e to the x, and the most general form is the plus c. Stepping back once more, antiderivative of e to the x is e to the x, antiderivative of a constant is a constant times x, plus a different constant for this step of the antiderivative. And stepping back one more time, antiderivative of e to the x is e to the x. Antiderivative of a constant times x is a constant times an x squared over 2. Antiderivative of a constant is a constant times x. And then there's the brand new constant. All right. An interesting application of this is going from acceleration back to position. We all know that if you take your position function and differentiate it, you get the velocity function. We know that if you take the velocity function and differentiate it, you get the acceleration function. And I'm accidentally bumping back and forth between variables here. Sorry. All right. Actually, I think t's going to be my choice. I'll stick with t's. Just messing up all the variables. T is the most appropriate. The point being, derivative of position is velocity. Derivative of velocity is acceleration. So what that means is, or at least what should happen, is the antiderivative of acceleration should be velocity, and antiderivative of velocity should be position. And it is. But the problem we're going to run into is, what do we do with these constants? It's okay if you're just finding just a general vague antiderivative for let the constants just stay constants. What if we need to know what these constants are equal to? What if that's important to us? Well, we have to be given some numerical values to work with if that's the case. For example, if I'm told that the second derivative of x is equal to a 2 plus a cosine of x. And they want to know what is the exact original function, not the most general form, but the exact function. Then I need more information to be given. I need them to tell me things like, well, f of 0 is equal to -1. They need to tell me that, for example, f of pi over 2 is equal to 0. All right, so how does that help? Let me show you. Let's back up one step. Antiderivative of f double prime is f prime. Antiderivative of 2 is a 2x. Antiderivative of cosine is sine plus an unknown constant. Now, they didn't give me anything that I could plug in for f prime, or I would make use of these numbers, so let's step it back again. F of x, antiderivative one more time. Antiderivative of 2x is an x squared. Antiderivative of sine is a negative cosine, so let me just show that here. Antiderivative of c is a cx plus some other constant of integration. So what am I going to do with that information? Well, the first thing I'm going to do is I'm going to plug in a 0. F of 0 would be a 0 squared minus a cosine of a 0 plus a constant times a 0 plus a C1. All right, and f of 0 has been given to me to be a -1. Well, this is 0, and what's this? What's cosine of 0? Well, cosine of 0 is 1, so that's a -1, plus that's a 0, and that's a C1, and therefore C1 is 0, so I can refine f of x to being x squared minus cosine of x plus cx, because I know the C1 is a 0. Now I can look at the pi over 2. F of pi over 2 is equal to pi over 2 squared minus cosine of pi over 2 plus a constant times a pi over 2. And I've been told that's 0. Well, cosine of pi over 2 is 0, so that zeroes out. This is a pi square over 4 plus a constant times a pi over 2 equaling 0. Moving the pi squared over 4 to the other side, constant times pi over 2 equals a negative pi squared over 4. Dividing off the pi over 2, I get that constant to be a negative pi over 2. So refining the function one last time, I find that f of x is equal to x squared minus cosine of x minus pi over 2 times x. All right, that is not a general form, but that is the exact function that has the second derivative we wanted it to have and has the function values here that were required or that were asked for. Okay, where this can be used, where this is commonly used, besides math, is in physics type situations. All right, very much applicable to physics. For example, if you are told that acceleration at time t is equal to t squared minus 4t plus 6, and you're told that the position, whoops, let me make it a little bit neater. The position at time 0 is equal to 0. In other words, starting from maybe like an origin, all right? And you're told that position at time 1 is equal to 20. Find the position function. Well, here's your acceleration function. Your velocity function will be a t cubed over 3, because that's the antiderivative, minus a 4t squared over 2, plus a 6t, plus a constant. And this is going to get in my way. All right? Plus a constant. Let me rewrite these. All right? Now, I could just call that constant c. That's what we've been doing. That wouldn't be a crime. But what you have to realize is that this is the velocity function. All right? And therefore, this constant should be given an appropriate name. And the appropriate name would be initial velocity. V naught, the V with the subscript of 0 means the velocity at time 0. And clearly, if I plug in a 0 right here, V naught's the only thing that's left. All right? Backing it up one more time. Position function. T to the 4th over a 12 minus, now notice this 4 over 2 would have reduced to just a 2, all right, just a plain 2. So it would be a 2t cubed over 3 plus a t squared, and I would put a 2 on the bottom. A 6 over 2 would just give me a 3 plus a v naught t plus another constant. What would be an appropriate name for this constant? It would be position 0. It would be position at time 0. All right, because I can come up here and say, well, S of 0 is 0 to the 4th over 12 minus 2 times a 0 cubed over 3 plus the 3 times a 0 squared plus a v naught times a 0 plus an S naught, and all that equals 0. Well, notice that this and this and this and this all 0 out. So that S naught is your initial position, and it's a 0. So I can revise this. S of t just became t to the 4th over 12 minus a 2t cubed over 3 plus a 3t squared plus a v naught t, and the plus 0, I'm not going to write that down, that's gone. All right, now S of 1 equals 20. So plugging in, S of 1 equals 1 to the 4th is 1. That's a 1/12. That's a 2/3 when I put in a 1. That's a 3. That's a v naught. That equals 20. All right, so because I'm feeling a little bit lazy, I'm going to take a 1 over 12 minus a 2 over a 3 plus a 3, turn it to a fraction, and I get 29 over 12. And then I'm going to take a 20, subtract over 29 over 12, turn it to a fraction, and what I find is that v naught is a 211 over 12. And 211 over 12, does that have a prettier form? Nope. 211 over 12 is where it's going to stay for me. So your position at time t is equal to a t to the 4th over 12 minus a 2/3 t cubed plus a 3t squared plus a 2 1/12 t. All right, there's your position function with all constants found, because they gave me enough values to be able to do it. They can give you either 2 position values to do this, or they could give you 1 position and 1 velocity, and you will do the same thing. All right, so there's an intro to antiderivatives, something that we're going to be using on a very regular basis. So start getting comfortable with them, and you're going to want to be able to do quite a few of them in your head.